Hello everyone, my name is Luke Bui. Today I would like to present you our paper about energy efficient web page loading. This work is a collaboration between researchers at Kai School of Computing and Microsoft Research Asia. As you know, web browsers are the core application on smartphones as they have high energy consumption. This is because they are kind of direct ports from their desktop versions. This figure shows the architecture of mobile Chromium web browsers. It's complex and identical to the desktop counterpart. Therefore, it's necessary to reduce the energy consumption of mobile web browsers on battery-powered smartphones due to the limited energy. However, we should not compromise the user experience because it's directly related to the revenues of companies. For example, 1 second delay in Bing search engine results in a 2.8% drop in revenue per user. Moreover, as users migrate to mobile, page load time is perhaps the most important metric we have. Therefore, the goal of this paper is to reduce the energy consumption of web page loading without increasing the page load time. Our approach is following. First, we analyze the architectures and behaviors of popular mobile web browsers like the open source Chromium and Firefox and closed source UC browsers on Android. It's worth note that the commercial Chrome web browsers is based on the open source Chromium web browser with some proprietary technologies. We identify energy inefficiency issues by looking to the overhead and redundant computation inside web browsers. We also look for the underutilization of heterogeneous architectures. We then develop energy-saving techniques to deal with the identified issues. Finally, we evaluate our techniques on top 100 US websites. The results show that our techniques save significant system energy while not increasing the page load time. We identify the following 3 energy inefficiency issues. The first one is the high energy cost of progressive web resource processing. This is because even for each small chunk of data, the whole data rendering pipeline must be executed immediately. For example, in our experiments, read system calls return only 1.3 kilobytes of data on average from network. Also, this causes high inter-process communication overhead, especially on multi-process architecture web browsers like Chromium between browser process and renderer process. The second issue is the unnecessary high painting rate. This is because web browsers tend to keep high painting rate even when visible screen changes can be very small during web page loading. In this paper, we distinguish the painting from the rendering. Rendering is a conversion from web resources like HTML documents into models in memory like DOM trees. And painting means the conversion from models in memory into the pixel to display on the screen. For example, when loading install.ram.com, which contains no animation, Chromium and Firefox keep painting rate at around 20 to 30 frames per second, while the UC browser even keeps the painting rate of a fixed 60 frames per second. More important, we found that 90% of paints generate zero visible changes on the screen in Chromium. This is because many of them are off-screen, outside of the report. The third issue is the underutilization of energy efficiently to cores on big little architecture. On big little architecture, a little core is very energy efficient. It's capable of reducing the energy consumption by a half compared to a big core at their highest frequency. However, current OS schedulers schedule stress based on load instead of quality of service. So schedulers tend to keep heavy stress on big cores rather than little cores. For example, when loading install.ram.com, Chromium and Firefox keep about 80 to 90% of thread time on big cores, leaving the little cores underutilized. We then rethink the energy performance trade-offs in web browsers. This is because energy consumption should be considered as a first-class citizen on smartphones. We aim to reduce the redundant computation inside web browsers by adjusting processing to the user-perceived content changes. Web browsers is designed to maximize the performance, so it keeps the maximum processing regardless of input data. Moreover, we also try to utilize the energy efficiency on heterogeneous architectures. We developed the following 3 energy-saving techniques. The first one is network-aware resource processing technique. It performs batch processing of web resources to reduce the overhead of small data sizes. It must deal with the trade-off between energy saving and the delay. For example, if we use a large batch size, then we can save a lot of energy, but with a high delay to the user. On the other hand, if we use progressive processing, then we will have lower delay, but with a high overhead. So we designed the batch size to be adapted to the downloading speed. So here we use the download speed as a lightweight approximation of content changes. This is because determining the content changes accurately require heavy analysis on dynamic contents like JavaScript. So we increase the batch size on fast networks to save more energy and decrease it on slow networks to reduce delay. So the batch size is determined by a buffer threshold, which is equal to an alpha factor times with the network output. So the alpha factor determines the maximum delay for a chunk of data to reside in the buffer, for example, half a second. The second technique is called adaptive content painting, which aggregates multiple content paints to reduce unnecessary computation on small visual chain painting operations. In this example, this technique aggregates the paint 1 and paint 2 into one paint A, because the difference between display 1 and display 2 is minimal. It also deals with trade-off between user experience and energy. For example, if we keep low frame rate, then we will save a lot of energy, but with worse user experience. And if we keep high frame rate, then we will have smoother user experience, but with higher energy consumption. So we design a paint rate parameter, which limits the maximum content painting rate. It dynamically adapts to content changing speed. Since determining the degree of content changing speed requires heavy analysis on contents like the dynamic analysis. So we use a lightweight approach. So we increase the paint rate parameter linearly when the content changes fast and decrease it to a minimum value when content changes slowly. We can estimate the content changes fast or slowly by looking to the layer 3 update signals from the rendering engine. The third technique is application-assisted scheduling, which better utilizes little cores on big little architecture. It leverages the internals of web browsers for scheduling threads. This is because web browsers know much more than the OS scheduler about their threads. So this technique can schedule threads according to the quality of service. So in the web browsers, QoS requirement is estimated as the frame painting time. So this technique uses a dynamic thread-to-core assignment. It moves threads to big cores when QoS is about to be violated. For example, when the frame painting time is lagging behind the QoS requirement, and it brings threads back to little cores when QoS is satisfied. For example, when the painting time is very fast, so we satisfy the QoS requirement in a stable manner. We implemented the techniques on a prototype based on Chromium version 38, which consists of 16 million lines of code. We modified 3 modules: the buffer resource handler for network-aware resource processing, the VSync monitor for adaptive content painting, and the thread management module for application-assisted scheduling. We also instrument the rendering engine to get the web page load time in the most accurate way. We evaluated the techniques on an emulated testbed for repeatable experimentation. We use a common 3G network condition with 2 megabit per second download, 1 megabit per second upload bandwidth, and 120 millisecond round trip time. We use a web page replay tool to record and replay web pages. The dataset is the top 100 website in the US by Alexa.com. We tested on 2 devices, one Galaxy S5 Exynos with a big LITTLE processor, and one Galaxy S5 Snapdragon with a symmetric processor. The metric is the page load time as defined in the W3C navigation timing specification. We also developed an automation tool to automate the experimentation so that each configuration and website combination is tested at least 5 times. So this video demo shows the comparison of performance between our device web browser and the different web browsers. The graph below shows the power consumption. As you can see, our revised web browser shows a similar web page loading speed to the default web browser, while it causes much lower power consumption. So it has the same page load time with the default one at 8.3 seconds, while it saves 40% of total system energy consumption. So we evaluated our techniques on top 100 websites. On Galaxy S5 Exynos with a big LITTLE processor, our techniques save on average 24% of energy, including the LCD screen. Moreover, our techniques decreases the page load time by 0.38% or 29 milliseconds in terms of absolute page load time. This is because our techniques reduce the redundant computation, so it even makes the page load time faster. On the Galaxy S5 Snapdragon phone with a symmetric processor, our techniques save around 12% system energy due to the lack of application-assisted scheduling technique. The page load time is increased by only 0.01% or 6.7 milliseconds in terms of absolute page load time. Among the 3 techniques, the application-assisted scheduling is the most effective one, while the other one have similar effectiveness. More important, page load time increase of the individual technique is small, with a maximum of 0.76% average increase of network-aware resource processing on Galaxy S5 Snapdragon. We also conducted a user study to evaluate the impact of our techniques on the user perceived experience. We asked 18 users to compare the performance between our revised web browser and the default web browser. On the first test, we'll ask them to observe loading speed and smoothness of 10 random websites. And on the second test, we let them to do real web browsing for 5 minutes. The results show that the users feel almost no difference between ours and the default web browser. Moreover, all users want to use our revised web browser either always or when low battery. We also conducted case study to analyze deeply how our techniques save energy. Analysis shows that our techniques have significant reduction of power consumption. For example, our techniques reduce the power consumption from 5.3 watt to 1.4 watt when loading inefficiency.com. Another analysis on application-assisted scheduling techniques shows significant increase of utilization of LITTLE cores on big LITTLE architecture. For example, this technique increases the utilization of LITTLE cores from 25% to 60% when loading inefficiency.com. We also did case study to analyze the effectiveness of other 2 techniques. So we find significant reduction of stress execution time. For example, the network-aware resource processing technique reduces the child thread execution time by 65% when loading inefficiency.com. We also did evaluation on various environments, just on fast network with 20 megabit per second download bandwidth, on 3G network when the 3G network interface is used, when loading web pages with cache content. And also we implemented our techniques on the Firefox web browser. The results show that our techniques are still effective on these various environments. with significant system energy saving without the page load time increase. Also, our techniques are applicable for other web browsers. Measurement on speed index metric show only slight increase with 1.8% on average. So it indicates very small slowdown in the visual progress. There are many related work on energy saving for mobile web browsers. Camelon on Mobi 6 2011 changes color web pages to save energy on OLED screens. Another work on 3W 2012 measure energy and provide guidelines for developers to reduce energy consumption of web pages, like to avoid complex JavaScripts. And more recent work on HPCA 2013 uses statistical inference models to save energy on heterogeneous architectures, but it ignores JavaScript and dynamic contents. Our work is different from others because it deals with trade-offs inside web browsers, while others focus on the characteristics of web pages. Also, our work is orthogonal with other approaches, so that ours can be integrated with others to further improve the energy efficiency. More important, our techniques were tested on real-world websites and smartphones. So in conclusion, in this paper, we identify energy inefficiency issues in mobile web browsers by looking to the overhead and redundant computation inside web browsers and the underutilization on heterogeneous architectures. We then proposed 3 energy-saving techniques and implemented them on popular mobile web browsers such as Chromium and Firefox on Android on commercial smartphones. Evaluation results on top 100 US websites show that our technique saves significant system energy while not increasing the web page load time. Thank you very much for your attention.